Epilepsy is one of the most prevalent neurological chronic diseases affecting people of all over the world and of all socioeconomic and ethnic groups, with around 5 million new cases every year. The disease is characterized by an enduring predisposition to generate seizures, which are defined as altered episodes of consciousness due to abnormal neuronal activity in the brain. Although epilepsy per se carries low mortality rates, the social and psychological impact that it produces in the patient makes it a meaningful global health issue. The most commonly used treatments are drugs, but these are ineffective in around 1 out of 3 cases. This is known as pharmacoresistant epilepsy, and in these cases, surgical resection is an option. However, this is invasive and potentially hazardous. Non-invasive techniques have been developed for these cases, being transcranial current stimulation one of the options that has shown efficacy towards epilepsy. It is often claimed, however, that these treatments are not personalized enough. In this context, hybrid brain models can play an important role. These brain models integrate both anatomical and functional features of the patient with the aim of having a personalized brain model. This personalized brain model, which mimics also epileptic activity, can be used to optimize and personalize in silico the treatment for a given patient. In fact, this is what is being done in the workflow of the European Galvani project, in which me, Esteban Félez, I am working in and developing my thesis following an internship in neuroelectrics. The aim of this thesis is to analyze different methodologies of personalizing the hybrid brain model. Functional connectivity can be extracted from the real brain by establishing statistical relationships between recorded brain signals. In our case, SEEG. This is intracranial electroencephalography. The same can be done using the signals generated from the model. By obtaining the functional connectivity of the simulated signals for the different model parameters and testing which resembles more to the empirical functional connectivity, the model would be personalized. This process is known as functional connectivity fitting, and it is what I am focusing on in my TFG. However, different methods of establishing the aforementioned statistical relationships between signals can be used, which also lead to different results. For example, cross-correlation phase-looking value, the nonlinear H2 correlation coefficient, and the nonlinear interdependence measure, namely L, will be tested in my case. Surrogate-built signals will also be used to see to which extent each tested metric outperforms the cross-correlation. In the end, the metric that provides better computational time, comprehensibility, reliability, and compatibility with simulated SEEG signals will be selected for the personalization pipeline, paving the way to future steps such as treatment personalization and optimization. Thank you very much.